Hello everyone. So today we are doing design of linear integrated circuit, practical number 3. Design of a practical integrator using an op-amp OP07. My name is Shah, SAP ID 6260001180031. The simulation tool we have used today is LT Spice. Our aim of this experiment is to implement an integrator using op-amp and to study its frequency response. So what is an ideal integrator? It is an op-amp integrating circuit which produces an output voltage which is proportional to the area, which is amplitude multiplied by time, contained under the contained under the waveform. An ideal op-amp integrator uses a capacitor C connected between the output and the op-amp inverting input terminal. The negative feedback to the inverting input terminal ensures that the node X is held at ground potential, that is virtual ground. If the input voltage is 0 volt, there will be no current through the input resistor Rin and the capacitor is uncharged. Hence the output voltage is ideally 0. If a, if a constant positive voltage DC is applied to the input of integrating amplifier, the output voltage will fall negative at a linear rate. In an attempt to keep the inverting input terminal in ground potential, conversely, a constant negative voltage at the input results in a linearly rising positive voltage at the output. The rate of change of the output voltage is proportional to the value of the applied input voltage. From the circuit, it is seen that node Y is grounded. Node X will also be at ground potential due to the concept of virtual ground, that is Vx is equal to Vy is equal to 0. Therefore, using the formulas and using integration, we'll get the value of V out as 1 upon R in C. Integration 1 is to 0 V in dt. Practical integrator. To avoid the saturation of the output voltage and to provide gain control, a resistor with high value of resistance can be added in parallel with the feedback capacitor CF. The closed loop gain of the integrator will be R2 upon R1, just like a normal inverting amplifier. Consequently, at low frequency of the input signal, the circuit behaves normally like an integrator. At high frequency, the capacitor acts like a short circuit and bypasses the resistor R2. The capacitor's resistance in turn reduces the gain of the amplifier. The frequency response of an AC integrating amplifier with DC gain control is shown in the figure below. At lower frequency of the input, the capacitor remains uncharged and acts as an open circuit. The result is the gain of R2 upon R1. As the input signal frequency increases, the feedback capacitor gets charged and almost acts like a short circuit, bypassing the feedback resistor R2. This results in the gain decreasingly linearly at the rate of 20 dB per decade. Therefore, for given Fa is equal to 1 kHz, Fb is equal to 10 kHz, and Cf is equal to 0.01 microfarad. Using the formula, we get the value of Rf as 15.9 kilo ohms and R1 as 1.59 kilo ohms. Here we have drawn the circuit of a practical integrator using the LT Spice simulation, and using this and different given frequency, we have found out the value of V out, the value of gain, and the value of gain in dB for different values of frequency. Now when we have a sine wave as an input, uh, we get when we have a sine wave as an input, we get an inverse cosine as our output. So we can clearly see that we are for an sine wave as an input, we are getting an inverse cosine as our output. Now when we have square wave as an input, So we can see for square wave as an input, we are getting an triangular wave as our output. Now when we have triangular wave as our input, here we can see that when we have a triangular wave as our input, we are getting an sinusoidal wave as our output. Now to find the frequency response, we change it to decade. So this graph shows us the frequency response, and the graph which starts from 16 dB, it shows us the phase response for the integrator. From this we can conclude that the above observation graph that the circuit works as an integrator until the break or corner frequency of the op-amp Fa is equal to 1 kHz. Beyond that the gain begins to reduce as we can see in the second graph, that is the phase response. The phase of the output voltage reduces with the increase in frequency of input voltage, which means the integration is not faithful to higher values of frequency. From the graph and observation, we can also conclude that FB occurs at approximately 10 kHz. That is when the gain becomes approximately equal to 0 dB. Beyond this point, the gain is negative. Furthermore, we conclude that on integration, a sinusoidal wave and inverse cosine wave, which we can see from the graphs. A square wave yields a triangular wave. A triangular wave yields a sinusoidal wave. Thank you.